In this video, we will look at how to multiply two vectors. So far, we have looked at how to add vectors, how to subtract vectors, and also how to scale vectors, that is, stretch them or compress them by multiplying them by a simple number. That particular process of scaling a vector is called the scalar multiplication. Of course, you don't have to multiply a vector by just a pure number. It could be a number along with units. For example, when we start to deal with force, we will see that what we are doing is multiplying the acceleration, which is a vector with units of meters per second squared, by the mass, which is a scalar, and which is measured in kilograms. When we multiply meters per second squared with kilograms, we get kilograms times meters per second squared, which is a Newton. The equation describing this is F is equal to ma. Notice that because m is a scalar, the direction of F will always be the same as the direction of A. And in fact, because m is always positive, they will always have the same direction and will not point in opposite directions. This is an example of scalar multiplication. We are scaling the vector A by the mass m to get another vector F. However, besides multiplying a vector by a scalar, you can also multiply two vectors. And there are two ways to do this. The first is called the dot product. Here we multiply two vectors to get a scalar. So our result loses any sense of direction. This is also sometimes called the scalar product. Obviously, do not confuse this with scalar multiplication. It is called the dot product because when writing the dot product of two vectors, you write A dot B. The other kind of multiplication of two vectors is called the cross product. Here the result is another vector. The symbol is naturally a little times symbol over there, a little cross, and so we write A cross B like this. The value of A dot B is given by magnitude of A times magnitude of B times cosine of the angle theta between A and B. Remember, we said that the dot product should give you a scalar, and in fact that is what we get. The magnitude of A is not a vector anymore, it is just a scalar. Similarly, the magnitude of B is not a vector anymore, it is just a scalar. And cosine of the angle, again, just gives you a number. If these are our two vectors, A and B, what do we mean by theta? Theta is the angle between A and B when you put them tail to tail. So remember, when trying to find the angle between two vectors, you do not put them head to tail or tail to head, you put them tail to tail, so they share a common tail, and you look at the angle between them. This is the angle theta between A and B. It turns out that for the dot product, it doesn't matter whether you measure the angle being from B to A or A to B. It will give you the same result either way. But supposing you are given two vectors and they are not tail to tail. Say these two vectors C and D. Well, your first option is to simply shift D so that it is tail to tail with C. Now that it's been shifted so it's tail to tail, it is clear that this is the angle between C and D. The other way to think about the angle between two vectors is that it is the angle through which you need to turn one of the vectors so that it aligns with the second one. What I am doing here is extending C with a little dashed line. This is the direction of C. If I want to turn C so that it aligns with D, I need to turn C through this angle. We can see that this is in fact the same as the angle that we saw before when D was placed over here. So remember, the angle between the two vectors is not this angle, it is this, the angle through which you need to turn C so that it aligns with D. Or equivalently, the angle through which you need to turn D so that it aligns with C. Notice that in the formula for the dot product, magnitude of A is always a positive number or 0. Similarly, the magnitude of B is always positive or 0. But the cosine of the angle can be positive, negative, or 0. In this situation, when the angle between the two vectors is less than 90 degrees, the dot product is positive. The sign of the dot product tells you whether the two vectors point in roughly the same direction, in roughly opposite directions, or are perpendicular to each other. Here, the angle between them is less than 90 degrees, and cosine of such an angle will be positive. And in fact, they are pointing in roughly the same direction. In this case, they are pointing in roughly opposite directions. The angle between them is greater than 90 degrees. In such a case, the dot product of A2 and B2 will be negative. And in this case, A3 and B3 are perpendicular to each other. There is a right angle between them, and in this case, cosine of 90 degrees gives you 0. They are neither pointing in the same direction nor in opposite directions. They are, we say, orthogonal or perpendicular to each other. Here's a question for you to try. Is the dot product of vector C and vector D positive, negative, 0? Is there insufficient information to decide? Can you not take the dot product of these two vectors? Or does it depend upon whether you do C dot D or D dot C? Pause the video and take another moment to think of the answer. We will now discuss the answer. We create a duplicate of vector C and then move it so that it is tail to tail with vector D. We can now see that the angle between C and D is greater than 90 degrees. And so, even though both vectors point to the right, since one points up and the other points down, they are pointing in roughly opposite directions. And so the dot product between them will be negative. To reiterate, since the angle between them is greater than 90 degrees, the cosine of such an angle which is greater than 90 degrees will be negative. And so the dot product is negative. Here is another question. This is a fairly straightforward one. What is the magnitude of the I hat vector? Again, pause the video and take a moment to think of the answer. We will now discuss the answer. Remember that the I hat vector is called a unit vector because its magnitude is 1. It is not 1 meter. The unit vectors do not have a unit attached to them as such. They don't have meters or centimeters as such attached to them. The unit there refers to the number 1, unity. And so the magnitude of I hat is simply 1. Remember that you can write the I hat vector in component form as 1, 0, 0, and then use the Pythagorean theorem to find the magnitude. Doing so, you would get 1 squared plus 0 squared plus 0 squared, which is 1, and the square root of that is 1. Here's another question. We have learned how to take the dot product of two vectors. If I give you some random vector q, what is the result when I do q dot q? Again, pause the video and take a few moments to try and figure out the answer by yourself. We will now discuss the answer. Using the formula we've learned for the dot product, we get that q dot q is magnitude of q times magnitude of q times cosine of the angle between them. But the angle between q and itself is just 0. Since the angle between q and itself is 0, we have cosine of 0, which is 1. The magnitude of q, remember, can be denoted as just capital Q without the arrow, right? With the arrow, it's a vector. Without the arrow, it's just a magnitude. So q times 1, which is q squared, which can also be written as magnitude of q squared. From the previous question, we have seen that for any vector q, q dot q gives you the magnitude of q squared. Thus, I dot I will give you magnitude of I squared, which is 1 squared, which is just 1. What is the value of I dot k? Pause and take a moment and try and figure out the answer by yourself using the formula for the dot product that we have already learned. We will now discuss the answer. I dot k is magnitude of I times magnitude of k times cosine of the angle between them. Since I is a unit vector, its magnitude is 1. K is also a unit vector, its magnitude is 1. And the angle between them is 90 degrees, because I lies along the x-axis and k lies along the z-axis. Cosine of 90 degrees is 0, and so I dot k is 0. This makes sense because we know that the dot product of two perpendicular vectors should be 0, and I and k are indeed perpendicular. To summarize the dot products of the various combinations of unit vectors, we see that I dot I is 1, j dot j is 1, and k dot k is 1. This is because I dot I will give us magnitude of I squared, similarly k dot k will give us magnitude of k squared, and these are all unit vectors and their magnitude is 1. However, I dot j will give us 0, j dot k will give us 0, and k dot I will give us 0. This is because the dot product of two perpendicular vectors is 0. Another useful thing to remember is that cosine of minus theta is equal to cosine of theta. So for example, cosine of 320 degrees can be written as cosine of 360 degrees minus 40 degrees, or cosine of minus 40 degrees, but that will be the same as cosine of 40 degrees. Because of that, it doesn't matter whether you measure the angle as going from vector A to vector B or from vector B to vector A. And thus, A dot B is the same as B dot A. So if K dot I is 0, then I dot K is also 0. Let us try another way of calculating the dot product. Let us consider vector C, which is 7i hat minus 2j hat, and vector D, which is minus 3i hat minus 6j hat. And we will calculate C dot D. what we will do is FOIL the product. We multiply the two I terms together. We multiply the I and j term together, then the j and I term together, and then the two j terms together. We have foiled it and written it out over here. However, I.I is 1, I.j is 0, j.I is 0, and j.j is 1. This simplifies to negative 21 plus 12, which is minus 9. Notice that the only products we really needed to pay attention to were the products of I with I. 7 times minus 3 gives us minus 21. And j with j. Minus 2 times minus 6 gives us positive 12. And then we add those products. Negative 21 plus 12 is negative 9. This leads us to another formula for the dot product. If vector A is axi hat plus ayj hat plus azk hat, and vector B is bxi hat plus byj hat plus bzk hat, the dot product of A and B is axbx plus ayby plus azbz. Again, remember, the result of the dot product is a scalar. Notice that the final answer does not contain I hat, j hat, or k hat. It is just a number with units. To summarize, these are two different ways of calculating the dot product. If you know the magnitudes of the two vectors and the angle between them, it is easier to use this formula. If you are given the two vectors in component form, it is easier to use this formula. Let's get some practice with this new formula for the dot product. Try and find the result of 3a dot b, where a is given by this vector and b by this vector. Pause the video and try and work this out and see which of the answers you get. We will now discuss the answer. Before we look at the actual solution, we notice that one of the possible answers can be eliminated straight away. Option B here is not a scalar. It is a vector, but we know that the result of the dot product should be a scalar. So option B can be eliminated right away. When doing the product 3a dot b, you can either do a dot b and then multiply by 3, or you can calculate 3a and then take the dot product with b. Either way will give us the same answer. I choose to leave the 3 outside and multiply it at the end. Taking the dot product of these two vectors a and b, again I multiply the x components. 5 times 3 is 15. I multiply the y components. Negative 2 times positive 4 is negative 8. Vector A had a z component. Vector B did not have a z component, and so I write the z component of B as 0 k hat. Negative 3 times 0 is just 0. We have 15 minus 8, which is 7, and times 3 is 21. We will revisit some of the results we derived earlier, but now using the new formula. We can write I dot j as 1i hat plus 0j hat plus 0k hat, dot product with 0i hat plus 1j hat plus 0k hat. And the result we see is 1 times 0 plus 0 times 1 plus 0 times 0, which gives us 0, which is the same result we got before. Similarly, for an arbitrary vector v, v dot v becomes vx plus vy plus vz. But that is vx squared plus vy squared plus vz squared. But that is the same as square root of vx squared plus vy squared plus vz squared, the whole thing squared. But this square root is the magnitude of v, and so v dot v is the magnitude of v squared, which can be written as v squared without the arrow. Now that we have two formulas to determine the dot product, we can use this to find the angle between two vectors. Remember that a dot b can be expressed in two different ways. One is magnitude of a times magnitude of b times cosine of the angle between them, and the other is ax bx plus ay by plus az bz. Since we want to find the angle, we set this side equal to this side and solve for cosine theta. So first we set this equal to this and solve for cosine theta, so that gives us cosine theta is equal to a dot b divided by magnitude of a, magnitude of b. Now using the other formula for a dot b, we have cosine theta is equal to ax bx plus ay by plus az bz divided by magnitude of a times magnitude of b. As an example, we will find the angle between vector c and vector d. The solution is pretty straightforward, so I won't go over it line by line. Remember to use the forums if you have any questions. That is the end of this video. I'll see you in the next one.